In this video, we're going to talk about how to use the process tool created by Andrew Hayes in order to evaluate moderation effects in SPSS. Make sure you download and install that tool before we begin. All right, now that you've got that tool installed, let's take a look at SPSS. So I'm got a subset here of the PISA 2012 data. And let's say we're interested in understanding whether there's a moderation effect between SES moderates the relationship between students' enjoyment of mathematics, self-reported, and their mathematics achievement as measured by the PISA 2012 math test. So I have dichotomized enjoy math variable here from the original variable, which is here, which you can see there were 4 options. So I dichotomized it where 1 and 2 became a 1. So 1 means agree that they enjoy mathematics. And a 3 and 4 became a 0, meaning they don't agree. They don't like math. And then PV1 math, I'm going to use as a estimate of students' mathematics achievement, just the first possible value here. And then ESCS, which is PISA's measure for SES. So if you go to Analyze and Regression, once you have that process tool installed, it will show up as an option. We select this. PV1 math is our outcome measure. Enjoy math is the independent variable, the main focal predictor. And then SES, or PISA's measure for this, ESCS, is the moderator variable W. Under options, you can check this box here to generate code for visualizing interactions. Depending on what version of SPSS you have, this may or may not work well. And I'll show you how to do this in Excel in order to get the values more the way that we would want to see them, in case it doesn't work in your version of SPSS. The conditioning values, I'm going to choose 1 standard deviation below mean and 1 standard deviation above, because SES is already set up to be standardized, and it is centered at the mean of all the countries that participated in PISA 2012. So you could recenter that here in this section. And then I'm going to grab the Johnson-Neyman output in order to get a better idea of where things become statistically significant or not. Okay, click Continue, click OK. And then we're going to have to wait a minute. It takes us a little bit to run because that Johnson-Neyman output is a bootstrapping method that's going on here. So if we just give this a couple more minutes to run. All right, so once you do that, it comes out to look like this. Let me make this a little smaller here so we can see. You can see up here, this is what we put in. We have a sample size of 42,553, so we need to be careful about assuming that a statistically significant result is truly statistically significant or not. This might be inflated. The R-square value, 23%, that's decent but not great. And you can see it is statistically significant. The coefficients table here, enjoy math, has a coefficient of 13, meaning the difference between enjoy and don't enjoy is 13 points. For context, the standard deviation in PV1 math is around 90 points. So a difference of 13 is quite small, despite there being a statistically significant result for that coefficient. SES, of course, being the highest, and then the interaction, which down here you can see enjoy math times SES. Quite a small coefficient here of just under 3 points. So if I am trying to understand a moderator, I would say at this point, it's not likely that it's much of a moderator. It is statistically significant. The R-squared change is around 0.04%, very small despite its statistical significance. So once again, further evidence that maybe this SES as a moderator between enjoy math and math achievement is not that great of a moderator. The conditional effects, remember we chose 1 standard deviation below and 1 standard deviation above. So negative 0.3, that is the average SES for the specific subset that I used. And so negative 1.55, that is 1 standard deviation below. 0.9429 is 1 standard deviation above the mean. All of those are statistically significant, and we see here that at a value of SES of negative 3.22, which is just above 1% of the data possible below that, that is where the change happens from statistically significant and statistically not significant. And if you scroll down, you can see which direction that change goes. So here's negative 3.22, at which point the p-value is 0.05. Below that, it is not statistically significant. And above that is where the statistically significant region is. So above an SES value of negative 3.2, the difference between students who enjoy and do not enjoy mathematics is statistically significant, but below that it is not. This brings further clarification that probably SES is not moderating this relationship, because there is very few students who are below negative 3.2, especially if we were to look specifically at this data set. But if we're thinking about the larger population, it's an extremely low percentage of people. It's probably not much of a not an important moderator. If you scroll down, you can see this data here. This syntax, if you copy this syntax from data list free all the way down to the period after enjoy math, paste it into a syntax window, and then run that. Depending on what version of SPSS you have, you will get 2 different lines, one for students who don't enjoy, another one for students who reported that they enjoy math, and their scores based on different levels of SES. And it's only going to show you 1 standard deviation below the average and 1 standard deviation above here. So it doesn't show you that much, especially since we know that it becomes statistically significant. To see the change, you have to go back to negative 3.2. So you have to go quite a ways down below negative 1.55. So if we want to do this in Excel, what we have to do is copy this piece and then just extend the bounds, but we have to reformat the data a little bit in order to get the correct result here that we want. So if we look at Excel, when we translate that over, it's going to look like this. There was enjoy math, SES, and math scores, and enjoy and don't enjoy were not separate columns, but they showed different math scores for each different level of the enjoy math and each different level of SES. So if we want to put this in a line plot in Excel, we have to change the format a little bit. So you can see here what I did is, if you think about this and separating that into 2 columns, enjoy and don't enjoy, -1, by the way, it's putting this little supposed error here. It's telling me, hey, this is a number and you stored it as text. Well, if you can see up here, I put a single quote in front of the -1 so that it would view it as text. That's what we want, so that Excel recognizes it as a label rather than a value. So here, -1, enjoy math is 410, Don't enjoy is 419, so I split those up and put them like this. The same with average. Enjoy and don't enjoy, 454 and 466. I split them up this way for average, and then for positive 1, 498 and 513, I split them up across two different columns. And because this is a linear model, we can simply take this and I'll show you what's going to happen here. I can delete these here and here. And then we just want to tell it to continue this trend, this pattern. The difference between these are the same. So if we extend this to below, it extends the pattern that way, and then if we drag it up, it extends it below it. And we want to do this, and remember it went down actually past -3, so let's add also a -4 here. And you need to grab, I usually grab 3 rows in order to make sure it picks up the pattern correctly. And extend that down. Whoops. One more. And I'll also extend it up this way to +4 just to keep the trend equal on both sides. Make sure to put that quote in there so that it sees it as text and doesn't try to type it in as just 4. Because we want this to be viewed as 4 standard deviations below, 4 standard deviations above. All right, now if we grab this and go to insert, and we don't want scatter plot, we want this one that looks like lines. And let's do a stacked line chart here. And let's make sure that it did this right. So -4, 278 for both of these. And for some reason, it didn't grab the data correctly. Let's try again. So that should be the intersection point there at 278. Let's pick this first one here, line. There we go. So if you use the line chart, and this is going up to 700 down to 0. We don't need it to go that far. So if you click on this, we should be able to format the axis. We don't want the minimum as 0. The minimum value is 278, so maybe if we put in 250, and the maximum value was at 654, so I'll do 675 and see if that helps us get a better view, be able to see more of the difference here. That does help a lot. And you can see the values here are changing by this -1, -2 average all the way up. And then of course you can add a chart title, you can add axes titles, and then you have a nice little picture. And the point at which it becomes statistically significant is right around here. So you could add a little line, and I would just probably do that in Word, add a dashed line here at around -3.2 to show that after that it becomes statistically significant. However, as this picture makes pretty clear, it doesn't look like the difference in these values becomes that important until much later, which could be a result of the large sample size. You can also see that here. If we had a difference column, for instance, we could see that if we subtract these two. And then copy that down. You see that the difference does not become very big until towards as they start moving farther apart. So even though they become statistically significant right before this difference of only 3 points, it's probably better to consider these points in the larger range to be the more important differences to look at. And that's all I've got for the process tool. Let me know if you have any questions. Have a great day.